Okay, so this is video 2 on rational functions, and I wanted to take you a little bit deeper into some of the concepts involved. And it involves a lot looking at a lot of different graphs and sort of examining some of the features of those graphs. The graphs that I'm going to do, I think, are down here in the left sidebar. And so if you get bored, if you get stuck, if this is going too slow and you want to think to yourself, what are these pictures going to look like? You are more than welcome to do that. I'm going to reveal them to you one by one and show you some of the analysis underlying the graph, I guess. So the first one is just y equals x minus 2. Maybe you can already picture that. This is the picture of a line. What's important about that line? It's got a slope of 1. It's got a y-intercept of 2 comma 0. So now I'm going to graph 1 over x minus 2. Notice the last one wasn't really a rational function. That's just a polynomial of degree 1. This is a rational function. And also what's important is that it's the reciprocal of the original line that I showed you. So you may, from our last class, be able to picture what this is, which is a graph with a asymptote, and the asymptote is at x equals 2. And I'm gonna just show you that asymptote. I'll make it orange. I'll make it dashed. This thing has an asymptote at 2 because the denominator of a rational function can never equal 0. And the closer it gets to 0, the more the function explodes. And so that's why you see a vertical asymptote is x equals 2. And also, since it's a ratio and the function with the higher degree is on the denominator of this function, you notice that as you go out towards infinity, the function approaches 0. And as you go out towards negative infinity, the function approaches 0. But just notice the relationship between a function and its reciprocal, because this is something we get into in the second semester. But where this function was linear, right? This was the original function, where it had a, what do we call this? An x-intercept, where this function, the original function, had an x-intercept. The reciprocal had an asymptote. That's going to be true. That's going to always be true because we're talking about reciprocals. Reciprocals involves dividing. Where the original function, the red, went to infinity, the reciprocal went to 0. But it stayed positive, okay? So this went to positive infinity. This went to 0 from the positive side. This function went to negative infinity. The reciprocal went to 0 from the negative side. All right, that's it on reciprocal functions. That is a topic for a later time, but I thought maybe just introduce it to you a little bit. All right, so picture yourself, close your eyes, think to yourself, what's this next function going to look like? Boom, there it is. What does it look like? Well, it looks like it's got an asymptote. Where is the asymptote? You might say to yourself, well, that has an asymptote at x equals 2 because it has a denominator of x minus 2. And if so, you'd be correct. I like my asymptotes to be dashed, so I'm going to make that dash. You also might try to think of, what does it look like when it's close to the asymptote? Well, it looks kind of parabolic, close to the asymptote. Well, what does it look like far from the asymptote? Well, it actually looks like a line. And so it looks like the line of x plus 5. And so we call x plus 5, this concept has a couple different names. One of them is a slant asymptote. And it's a slant asymptote because it's slanted and because further away from the forbidden area of the denominator, which is 2, the function gets infinitely close to that slant asymptote, both on the positive side and on the negative side. It's also called an end behavior function. And that's a fancy CPM term that you learn in pre-calculus and review in calculus. But the end behavior of a function, like the end behavior is what's this function doing in the tails. So in this particular case, the function is going to infinity on the right. It's going to negative infinity on the left. But what's the end behavior function is along what path is it following that line. So the end behavior function in this case is it's going along the path of x plus 5. And you might wonder, how do I get x plus 5 from that? Well, to get x plus 5 from that, you have to do a little thing that I call polynomial division. Polynomial division is one of those things that I don't tend to do anymore because it's below my pay grade. But for you guys, I did some polynomial division. And I did x minus 2 goes into x squared plus 3x minus 5. And I got these two parts, x plus 5 over x minus 2. And if you think about what end behavior means, it means when I'm plugging in like a really big number, like if I plug in 1 million for x, what happens to both of these parts? Well, this part gets really, really big. And this part right here, the denominator is going to get really, really big. As the denominator gets really, really big and the numerator doesn't change, this part goes to 0. So that's why there's one part when you do polynomial division that ends up being the slant asymptote or the end behavior function. And then the other part, which is the part with the remainder, that sort of gets muted as the function gets further from that forbidden zone. So if you want to see what that looks like, I had x plus 5, and that gave me the slant asymptote. But if I added this part plus 5 over x minus 2, I get the same exact function. Notice that these two, the orange and the black, are the same exact function. If I didn't have this one dotted, then you wouldn't even see the orange because the black would be on top of the orange. Okay. And also notice that in this one, when we started, we had a degree 2. We had a quadratic on the numerator and a linear function in the denominator. So because the degree was higher in the numerator than the denominator, that means that the numerator grows faster, which is why you have the function going to infinity on both the right and on the left. If I inverted this, if I put x minus 2 on top and I put x squared plus 3x minus 5 on the bottom, I would have a function that it doesn't go to infinity on both sides. I would have a function that goes to 0 on both sides. Like if I said y is equal to x minus 2 divided by x squared you can see that this function has some things similar, but I don't need to compare them too much. But just notice that these functions are reciprocals of each other. The same thing would be true. This one has asymptotes where this one has zeros, but I think those are irrational zeros. But also where this one went to infinity, this one goes to 0 because that's the nature of a reciprocal. All right. So then picture now. I don't want you to think too hard of this one. I want you to think of what this one looked like, and I want you to picture what this one's going to look like because it has the same format as this one. So let's graph this one, and let's see. Whoa! I bet you were picturing a vertical asymptote at -2, such as the vertical asymptote that we had at +2 here. Is there a reason why this one doesn't have a vertical asymptote? Well, let's go look and try to find out what that function equals at 2. It looks like it equals 1. We can get closer and closer and closer to it. And, oh, there it was. Oh, it says undefined. Why would it say undefined here? Why wouldn't it exist? Well, think of what happens when I plug in -2 to this denominator, you get 0. And to the numerator, well, -2 squared is 4. 4 minus 10 is -6. -6 plus 6 is 0. And so this is kind of an important concept for this particular function. When I plug in -2, I get 0 over 0. 0 over 0 does not equal 1. It does not equal 0. And in fact, it doesn't exist. It doesn't exist. It doesn't exist. It doesn't exist. Okay, so that's why we had, it would take me forever to find it, but you saw it before. That's why we have a hole, which Desmos doesn't really show you the hole, but there's a hole because it's undefined, which means that it exists at every point to the right, but not at any of the points to the left. That's why we have that there. And if you want to know how you can mine for a hole in a rational function, well, what it involves is factoring. And if a rational function like this factors, and you can cancel a factor from both the top and the bottom, like you can in this case, that means you're going to have a hole at the x value that makes both of these things 0, because you're going to have 0 over 0. And you can think that this is functionally equivalent to the function y is equal to x plus 3, but technically they're not exactly equivalent. I know that if I make, let's see, I can do the same thing. I can make this one dotted so that you can see them both, and they do look like they're exactly the same. However, on this dotted line, if I go to -2, I get a value, which is 1. So the only two times these functions are different is at that point, -2, where the red has a hole that's undefined, and the blue dotted has not a hole. All right, so then let's go get a little deeper into the wormhole here. Now I have another rational function, and I want to talk about the concept of end behavior function. You might start looking at this and you might think, what does that look like? And you're probably like, I have no idea, and that's fine, so I'll show it to you. It looks like this, and let's zoom out a little bit more and let's see what we're looking at here. And it looks like something that the y changes a lot quicker than the x. So let me just maybe make the x vary between maybe -15 and 15, so we can see it kind of good, and the x can do what it's going to do. And notice that it has two asymptotes, two vertical asymptotes. You might be like, where are those vertical asymptotes? And your first instinct should be, well, what would happen if I factored the denominator? If I factored that denominator, I get x minus 3 times x plus 1, which once it's in factored form, you can easily identify or infer what the vertical asymptotes are going to be. It's going to be at x equals 3, and it's going to be at x equals -1. Let's go with that color because there's a little bit more contrast. And then you're like, that's it, right? But also, you might wonder, what does this function do when it's going? What does the papa function, the mother function, the original function, this one, do as you're getting further from the asymptotes? What lines, what path does it follow? And it actually looks like a quadratic. And so this is the idea of the end behavior function here, is this quadratic that I have, x squared minus x minus 1, is not the same exact function as the one that you're looking at most of the time. However, as you get further away from where the forbidden areas of the denominator are, which is at 3 and -1, the functions become identical. There's one right on top of the other. And I could add some other stuff to this to make them exactly identical. And I just want to show you again, because the key to finding these things is polynomial division. Polynomial division is something that I feel is below my pay grade. Teachers do a lot of things because we had to do them ourselves, so students are required to do them. Polynomial division is one of them. I would almost never do a polynomial division problem of this length because I experienced trauma doing it as a student, and I don't want to go back to that trauma. But for you guys, I did. And here's where I found the end behavior function. And the other part is the remainder right here. And if you think about what that remainder is going to look like in another way, it could be -5 over x minus 3 times x plus 1. What would be true of this function? Just this part here, well, it would have vertical asymptotes at 3 and at -1, excuse me. So if I want to make it exactly identical, I can do -5 divided by x squared minus 2x minus 3. And now they're exactly identical. And this is an introduction to a lot of the different concepts that are oscillating inside your head when you're thinking about rational functions, and it's going to take some time for all these things to settle down. And I went further than I normally would do because we're in a distance learning environment. But I think one of the things that you should be aware of is that you look at a rational function algebraically, and now you want to associate some of the features on a graph. But one thing that you always want to do is you want to compare the degree in the numerator to the denominator, because that's going to give you your first insight into what the end behavior of the function is. So what I mean by that, when I look at letter A here, I immediately notice that the degree of the denominator is cubed, the degree of the numerator is squared, and I immediately know that the denominator is going to grow faster, which means the end behavior is going to go to 0. If I have a situation where the numerator is higher than the denominator, like in this, x cubed over negative x squared, then I know that the numerator is going to grow faster than the denominator, which means in the ends, in the tails, we're going to go to infinity or negative infinity. If I have a situation like this, where the degree in both the numerator and the denominator is x cubed, what I can think of doing when I'm thinking about the end behavior, this one's going to have an end behavior. It's going to have a horizontal asymptote of x equals 5. And if you think of why that is, the limit as x goes to infinity of 5x cubed over x cubed equals 5. And so what the process you want to think about doing is, when you're talking about end behavior, the term with the highest degree overrules every other term that's in that expression. Not closer to 0, not closer to the forbidden areas, but in the end behavior, that's going to be the true case. So you're going to do some practice with those today. I encourage you to use Desmos to think about things in your head and see how far you can get to, and then go to Desmos and then see what it looks like, and then compare how you originally thought it was going to be with what it actually looked like, and try to talk to your group about coming to terms with some of those disparities.